Okay, so let's open your precalc books. We're on page 52 of your precalc book. We're going to start doing the difference of squares problems, and then after that, so we're starting with problems 35 through 43 on page 52. So we're on page 52. 35 through 43, those are the difference of square ones. We're going to do only the odd. After you do that, we're going back to do 1 through 7 greatest common factor. So we're doing it in the order we covered it. 35 through 43, and then 1 through 7. It shouldn't take too long. So you're taking the square root of the first term, the square root of the second term, plugging it into the equation x minus y times x plus y. So you have your equation x minus y times x plus y. That's right. That's right. Just go to the next one. So for 1, we have x minus 3 times x plus 3. With 35, 37, we have 2a minus 7 times 2a plus 7. We have 1 minus 10x times 1 plus 10x. Square root of 100 is 10. Square root of x squared is x. (41) we have x squared minus 3 times x squared plus 3. 43 is the hardest one. You're taking the square root of x minus of x plus 5 squared. It's just like the one I did with you in class. And then you're taking the square root of 4 and you're plugging it into the equation and you're combining like terms. So the square root of x plus 5 squared is x plus 5. Square root of 4 is 2. You plug them into the equation, x minus y times x plus y. You combine like terms. Okay, now just combine them. Okay, so we have x plus 5 minus 2 times x plus 5 plus 2. You combine those to get your answer. And then after that, you go up to 1. So 5 minus 2 is 3. 5 plus 2 is 7. You get x plus 3 times x plus 7. Gosh, that's hard to read. Okay, now we're going all the way up to 1. You're pulling out your greatest common factor. Number 1, what do they have in common? It's just a 5. You pull that out, you get 5 times x plus 4. What you have left is x plus 4. So you should be able to multiply it out, get back to where you started. Oh. 8 is in the factor. Yeah. For 3, what is the factor of 15 and 12 that they have in common? That's 3. So you're pulling out a 3x. Now you can pull out a negative. If there are two negative terms, they often pull out a negative. So in that case, we have negative 3x. They pull out a negative. It's simpler than having the two negatives there. So we have minus 3x times 5x plus 4. You pull out the lowest power of x, the lowest power of y, and see what you have left. For 7, you look at those two terms and you pull out what they have in common. You pull out 1x, so how many x's do you have left? 1. You pull out your y, okay, go on to the next one. Pull 2 from 6, what do you have left? Okay, you pull out your x, you pull out your y. 2 from 14. Okay, so 5, we pull out 2xy, we have left 5x plus 3 minus 7y. Show me if you got 7. Show me if you have 7. 7, you pull out x minus 3. That leaves you a plus b times a plus 3b. That's what we pulled out, the x minus 3. Then you combine like terms. X minus 3 times 2a plus 4b. Okay, that's it. Now, if you had gone through this and finished everything early, you can start the even, but you don't do the even in class, and then especially when you're not keeping up with us. So you do the even either when you're done with all your odd or for homework. So your homework is to do the even. Okay, now we're going to talk about factoring by grouping. So we're doing a lot of factoring things today. Factoring by grouping is related to what we just did in 7. Okay, so you're given these like expressions, 2 expressions in that situation where you pull out what you have in common. That is factoring by grouping. We're going to go through that. You factor by grouping when you have 4 terms. They brought you to the second step. We're going to start out with the first one. So everybody understand your homework? It is 2 through 8, and then 36 through 44. Okay, now So when do we do factoring by grouping? It's when we have we've given 4 terms. Okay, so if you're given 4 terms, that's when you're factoring by grouping. So let's say, for example, we have 6xy plus 14x minus 12y minus 28. You pull out the greatest common factor from the first 2 terms and the second 2 terms. So usually they set these problems up such that the first 2 have something obvious in common and the second 2 have something obvious in common. Sometimes it works where you can reverse them and they still have something in common, or sometimes you have to change them around, but not usually. Okay, so they give you 4 terms and you pull out the greatest common factor from the first 2 and the second 2. So there's not, we could pull out a 2 from all of them, but that wouldn't get us very far, okay? That would be all we could pull out from the 4 of them. But you should know when you see 4 terms, what you're doing is factoring by grouping. So from the first 2 terms, we have 2x. That leaves us 3y plus 7 left. From the second 2 terms, now you might have thought to pull out only a 4. If you pull out only a 4, you'd have minus 3y minus 7. The way they set up the problem, whatever you pull out gives you the same thing in parentheses. So if you didn't get the same thing in parentheses, something went wrong, okay? So if you look at it, and these are both negative and these are positive, you just need to pull a negative out. So what we want to have is the same thing in parentheses, so we can pull that out as our greatest common factor. So you must have the same expression in parentheses. Now this was similar to that last problem. So what do they have in common? They have 3y plus 7 in common. So you pull out the 3y plus 7. And then what do you have left? You have left this 2x and this minus 4. So what we have is 2x minus 4 times 3y plus 7. So we factored by grouping. Now, some of you who learned the AC method for factoring a trinomial, you would have done some factoring by grouping. Okay, so whatever you have left here and here, that goes in the other parentheses. It doesn't matter which order. Are there any questions so far? Okay, let's see you do this one. 21xy minus 35y plus 18x minus 30. So you look at the first 2 terms, 21 and 35. Look at what factor they have in common. X, Y, and X, what do they have in common? Then you look at 18x and 30. What do they have in common? Okay, now do the same thing here. You should do the same thing in parentheses. If you didn't get the same thing in parentheses, something went wrong. So once you get one thing in parentheses here, so you pull out the 7 and you pull out the y. And what you have left here, you have the 3x. And then 7 times 5 is 35. So now, whatever you pull out here, what do 18 and 30 have in common? pull that out, and you should have the same thing left. If you don't have that same thing in parentheses, something went wrong. So if you pull that out and you get 3x minus 5, you know you want to have 3x minus 5 on the other. So what do you pull out of 30? We're pulling out a 6. Because we know if we pull 6 out of 18, we'll have a 3. If we pull 6 out of 30, we'll have that minus 5. Now, once you have that, you can pull out your 3x minus 5. Okay? When you pull out the 3x minus 5, what do you have left? Abigail? Right, you pull out the 3x minus 5, what you have left is 7y plus 6. Okay? All right, let's go to the next one. Let's see you do this. 21xy plus 18x minus 35y minus 30. Actually, you'll get the idea why I'm doing it. This should look familiar, right? We're doing the same problem in a different order. So 21xy plus 18x. So pull out what 21xy and 18x have in common. And then pull out what minus 35 minus 30 have in common. So 21 and 18 have 3 in common. X, Y, and X have X in common. So you're pulling out a 3X. When you pull out the 3X, you look at what you have left. You should have that same thing in parentheses when you pull it out of the next one. Now for this problem, we can reverse the order and get the same answer. It doesn't always work well. So you pull out the 3x and you get 7y plus 6. Now that should look familiar, right? You can probably guess what we're going to pull out of the next one just by how we did the previous one. We need a minus 5 there. So if you pulled out a 5, you wouldn't have gotten 7y plus 6 in parentheses. You would have gotten minus 7y minus 6. So, that is my point, that if you're not getting that same thing in parentheses, something went wrong. And if you're off by a minus sign, you need to pull the minus sign out. So now we end up with the same answer we had before, 3x minus 5 times 7y plus 6. Okay, this is just showing you the same problem. We changed the order. Now they usually set it up for you where you want to just do it in that order. Here's one, 2x cubed minus 6x plus 4x squared plus 12. So what did 2x cubed minus 6x have in common? Pull that out. And then whatever you have left, you should be expecting you're going to see that in the other two terms. Minus 4x squared plus 12. So 2x cubed and 6x, they obviously have a 2 in common and x in common. Left here. You have an x squared left because we started with x cubed. Okay, so you pull out 2 and an x, that leaves you x squared there. Minus 3. So you get 2x times x squared minus 3. Now you know you're looking for x squared minus 3 in the other one. So you should be thinking, what am I going to pull out of that other one so I have x squared minus 3 left? And then after that, you pull out your x squared minus 3. So what do we pull out of the minus 4x squared plus 12? Anyone? Okay, good. Now we have to, if we pull out a 4, we're going to have minus x squared plus 3. You had to pull out a minus 4. Okay, you pull out the minus 4, so you have x squared minus 3. That way we can get x squared minus 3 in both of them. So as I said before, if your sign is off, pull out a negative. Okay, now we're going to go to back to page 52. We're going to do 9 through 13. You finish the odd, then you can start your even. So we're starting with 9, 3x cubed plus x squared plus 6x plus 2. Pull out what you can from the first 2 terms and then from the second 2 terms. So what do 3x cubed and x squared have in common? They have x squared in common. So you pull out an x squared. What do 6x plus 12 have in common? They have a 6x plus 2. They have a 2 in common. You pull out that 2. You go on to 11. We're on number 9. So we pull out the x squared, we have 3x plus 1 left. And you know you're looking for 3x plus 1 in the next one. So look at what you can pull out of the next one. Okay, so we pull out x squared, we have 3x plus 1 left. We pull out a 2, we have 3x plus 1. So then we pull out the 3x plus 1, we have 3x plus 1 times x squared plus 2. We go to 11. What can you pull out of ax squared minus ax? exactly. And we're going to have an x like that. And we're going to have a 1 here. So we pull out an ax on 11. That leaves us ax times x minus 1. On the next two, you can just pull out a b. You know, you're looking for x minus 1 in parentheses. So we have b times x minus 1. That gives us ax plus b times x minus 1. Go to 13. You finish 13, then you can go through the even. Six w cubed plus 4w squared. They have a 2 in common. Good. And what's going to be that? 3w plus 2. We'll have a more than w squared. Okay, now we go to the next two. We pull out a 2w squared, so we have 3w plus 2 left, so we know we're looking for 3w plus 2 in the next one. Since they're both negative, you know you're going to have to pull out a negative. So we get 3w plus 2. We need a 3w plus 2 in the next one. You want to pull out a negative 5. If you pull out the negative 5, then you have the 3w plus 2. Okay, then you combine them, so you get 3w plus 2 times 2w squared minus 5. All right, we're going to be going to physics now. So your homework is corresponding even. That would be 2 through 8, 10 through 14. So it's 2 through 14. And then we did 36 through 44. Okay, so these are all different types of factoring, and then we're going to do difference of cubes, and then we're going to do the general factoring over integers, and then we're going to put it all together. Factoring is just used all the time. It's used in calculus. You have to know factoring to be able to do anything in calculus or precalc. It's probably the most commonly used thing. Okay, so now we're going to go to, if you can open up your physics book, chapter 2. We're actually doing physics now, as opposed to the math behind the physics. So we're going to begin with describing motion. Motion is central to physics because, you know, basically everything involves motion. Describing motion. Newton's theory of motion. Okay, Isaac Newton is a famous physicist. So before we can accurately describe motion, we must provide clear definitions of our terms. So in physics, we have very precise definitions. The meanings of some terms as used in physics are different from the meanings in everyday use. So velocity and speed might be used interchangeably in everyday use, but they are not used interchangeably in physics. Acceleration is sometimes used in a way that it would not be used in physics. Precise and specialized meanings make the terms more useful in describing motion. So we have to go through what exactly are our terms that we're going to use for motion and what do they mean. Why do we need clear, precise definition? What's the difference between average speed and instantaneous speed? Speed and velocity. You can probably guess the difference between average and instantaneous speed, but you probably can't guess the difference between speed and velocity by the physics definition. So we're going to look at these and the difference between speed and acceleration. You might be able to figure out something in that one. So first, speed is how fast something is moving. Now you know that, but it is something more precise in physics. Speed is always some distance divided by some time. The units of speed might be miles per hour, meters per second, kilometers per hour, or inches per minute. Now we've been going through some speed things in physics class. We did kilometers per hour, miles per hour, meters per second. Average speed is total distance divided by total time. So the average speed is the different distance traveled divided by time of travel. Now write that down. You might think that is common sense, but it is different than our definition of velocity. Okay, so when we talk about physics, we need to distinguish between scalars and vectors. We were doing work with vectors where we said vectors have direction. So I want you to write down what we already talked about before. Vectors have magnitude and direction. Scalars have only magnitude. They have no direction. Okay, speed is a scalar. So if you talk about your speed as 70 kilometers per hour, that does not imply any direction. It doesn't tell you anything about the direction the person is going. Can you tell me another scalar that you might, for measurement, that has no direction, something else? We've used some of them already. What else would have magnitude but no direction? So time, when we talk about time of travel, that doesn't have any direction. Temperature, that we haven't talked about, but that would be a scalar. It has no direction. Convert 70 kilometers per hour to miles per hour. Why don't you do this? Now, I had you use 1.61, which is technically 1.609. Use this one, 0.6214 miles in a kilometer. We just divided 1.609, 1 by 1.609, so we got this. So instead of giving you the conversion of how many kilometers in a mile, I give you how many miles in a kilometer. So why don't you just do that, using your chain link conversion. Start with 70 kilometers per hour, put kilometers into miles using this, and then miles into hours. Okay, so start out with 70 kilometers per hour. And you know there's 0.6214 miles in a kilometer. Go through and multiply it all out in your calculator when you're done. And get your answer, and your answer should make sense. Actually, we're not changing time, we're just changing distance. So it's really pretty easy. There's just one step. Jaden, do you have it?
Yes. 43.5.
Good. All you had to do was multiply 0.6214 miles by 1 kilometer. So we canceled out kilometers. We get 43.5 miles per hour. Okay, now you see why we had to cover the chain link conversion. We're going through the step-by-step process. Okay, so we're convert 70 kilometers per hour to meters per second. Okay, so just do what you just got, which was you had 70 kilometers per hour. Now you're putting from kilometers to meters and then hours to seconds. Okay, 70 kilometers per hour to meters per second. You know how to go from kilometers to meters and hours to seconds. Okay, so there's 1,000 meters in a kilometer. So first step is to put 1,000 meters in a kilometer. And then you can go hours to minutes and minutes to seconds, or you can just go hours to seconds, just faster. 1 hour, 60 minutes, 1 minute and 60 seconds. But I had you do it just 3,600 seconds in an hour. It's a bit faster. You should get a reasonable answer. So you have 70 times 1,000. Naya, what do you have?
19.4 meters per second.
Good. We have 70 kilometers per hour. They did this in 2 equations, whereas I do it in 1. And then they multiplied that by 1,000 to get 70,000 meters per hour. And then they did the time in another level below, but I would normally do it in just 1. So 70,000 divided by 3,600 seconds in an hour, or they did it separately, minutes to hours, seconds to minutes. So you get 70 times 1,000 divided by 3,600 gives you 19.4 meters per second. Does everybody understand? Okay. Now, we're going to talk about average speed and instantaneous speed. I mean, you can figure out just from the difference between average and instantaneous what those differences are going to be. Average is an average over some period set of numbers, some period of time, and instantaneous happens in an instant. So the average speed, they give you this example from Kingman to Flagstaff. So we just said your speed is your distance traveled divided by the time. So 120 miles, 2.4 hours. They have an average speed of 50 miles per hour. Flagstaff to Phoenix, 54 miles per hour, the total trip. 120 miles. Now, it comes out exactly in the middle. It doesn't have to work that way. Okay, so for the first leg of the trip, it came out to 50 miles per hour, which was just distance divided by time. Similarly, for the second leg of the trip, and then they did the total trip where they added together all the miles and divided by the time and got 52 miles per hour. Now, as I said, it came out right in the middle, but it doesn't have to be that way. Okay. So this is speed. Now notice we didn't say anything about direction, whether it's moving east or west or south. So when we work with scalars, we don't have to work with vectors. It's a lot easier. When we work with a vector that has direction, we have to constantly pay attention to that direction, and we have to add vectors vectorially, which is different than adding them just algebraically. 3 plus 4 is 7 algebraically. Do you know what 3 plus 4 is vectorially? You'd have to use Pythagorean theorem. It'd be 5. Okay, rate is one quantity divided by another. Now you know that. Gallons per minute, pesos per dollar, points per game. So average speed is the rate at which distance covered over time. Instantaneous speed is the speed at that precise instant in time. Okay, that's what instantaneous means. Precise instant in time. It is the rate at which distance is being covered at a given instant in time. It is found by calculating the average speed over a short enough time that the speed does not change much. Okay, so you're limited by your instrumentation, so how are you going to figure out instantaneous? And we do this in the lab. What you do is you try to have a short enough time interval that the speed didn't change much. So that depends on how fast it's moving, right? If you have a turtle moving, you could have some significant range of time that still captures instantaneous speed, but it's not necessarily true for a rocket. Now, in the lab, with the equipment we have, we estimate it fairly well. So we try to have a small distance to have a small time, right? How do you do that so that you have a short enough time? You pick a short distance, and you get the time over that. So the speed shouldn't change much in a short distance. Okay, so we talked about average speed and we talked about instantaneous speed. I think you already knew the difference between average and instantaneous. It's the same idea. So we're going to be doing some labs to help you understand this stuff better by having you measure these things. Okay, what does a car speedometer measure? We have a choice here. Well, they haven't defined velocity yet, so it's not really possible for you to distinguish well between the two. But is it average speed, instantaneous speed, average velocity, or instantaneous velocity? What'd you say? Right. What we want to know for the speedometer is instantaneous. A speedometer measures instantaneous speed. They haven't yet defined velocity, so you couldn't say much about that. The speedometer tells us how fast we are going at a given instant in time. Which quantity is the highway patrol more interested in, average speed or instantaneous? What? The speed limit indicates the maximum legal instantaneous speed. So, if you're going over it by 20 miles per hour, but your overall average speed isn't over, that doesn't help you. They look at your instantaneous. And they do a lot of similar things. The radar gun, what they're doing is looking at the time it takes for that beam to travel that distance. So that distance traveled divided by the time gives them your speed. Velocity. Okay, so we're going to talk about what's the difference between velocity and speed. Velocity involves direction of motion as well as how fast the object is going. So velocity is a vector quantity. Vectors have both magnitude and direction. Velocity has a magnitude, the speed, and also a direction. Okay, so we've just been saying vectors have both magnitude and direction. Therefore, when we represent a velocity pictorially, you do it with an arrow. But the length of the arrow indicates the magnitude, and the direction points in the direction. A change in velocity can be a change in the object's speed or direction of motion. A speedometer doesn't indicate direction, so it indicates instantaneous speed but not velocity. Okay, you should write that down. A change in velocity can be a change in the object speed or direction of motion. So if something is moving and it changes either one, it changes velocity. So velocity is fundamentally different from speed, but the instantaneous speed at any time is the magnitude of the velocity. So if something's moving 20 miles per hour east, the speed is 20 miles per hour, and the velocity is 20 miles per hour east. So to get the magnitude of the velocity, you do use the magnitude of the instantaneous speed. But you have to have direction to have velocity. So if you were told 30 miles per hour northeast and you were supposed to represent that in vector form, you would have to draw your arrow northeast 30 miles per hour, okay? It would have both magnitude and direction, whereas if you were asked for speed, you would just say 30 miles per hour. Are there any questions? Okay. The car goes around a curve at constant speed. Is the car's velocity changing? Now I want everyone to write down on their paper yes or no. Got it? What's the answer? Anyone? Nobody confident? What'd you say?
Yes.
Yes, because the direction is changing. At position A, the car has a velocity indicated by the arrow vector v1. At position B, the car has a velocity indicated by the arrow vector v2 with the same magnitude, speed, but a different direction. Okay, so if you're changing direction, you're changing velocity, but there's no change in speed. Now notice how these vectors have the same length because the speed has not changed, but they point in a different direction, okay? A force is required to produce a change in either the magnitude, speed, or direction of velocity. For the car to round the curve, friction between the wheels and the road exerts a force to change the car's direction. For a ball bouncing from a wall, the wall exerts a force on the ball, causing the ball to change direction. We don't talk about forces till chapter 4. But what made something change? It was the force. So forces are central to mechanics physics, but we have to build up to how we can describe a force. In order to understand forces, we have to understand velocities and acceleration. Instantaneous velocity. Now, you can guess instantaneous velocity is a vector quantity having a size magnitude equal to the instantaneous speed at a given instant in time and a direction equal to the direction of motion at that instant. So we have magnitude and direction, and the magnitude is given by the instantaneous speed for instantaneous velocity. Now, so we have instantaneous velocity and we have average velocity, right? Similar to average speed, we can have an average velocity. These two vectors here correspond to cars of two different velocities. They have different magnitudes. So if either the magnitude or the direction changes, the velocity changes. Acceleration. Acceleration is the rate at which velocity changes. Our bodies don't feel velocity if the velocity is constant. Our bodies feel acceleration. The input to your brain is acceleration. If you had a velocity input all the time, you'd be going crazy sitting in your car or something or on a train. The input is acceleration, so you only notice when there is a change in velocity because that's all you need to notice. So write that down. Acceleration is the rate at which velocity changes. Acceleration can be either a change in the object's speed or direction of motion. Just like we just said, it's the rate at which velocity changes. And we said velocity has magnitude and direction. Therefore, you don't have to write down all this stuff on the bodies. But you need to write down this. Acceleration is the rate at which velocity changes. Therefore, acceleration can be either a change in the object's speed or direction. Any change in velocity is an acceleration. So that would be speed or direction. Now, you know yourself, if you want to turn around, you're going to have to apply a force. If you have an acceleration, you have a force. And if you have a force, you have an acceleration. So anything that causes a change in your direction or your speed, you're going to have to apply a force to change that. Okay, it's 10:30. Let's just do some homework here. These questions at the end of chapter 2 on page 34. Some of these I went over in the PowerPoint. I'm gonna give you questions 1 through 9, so you can start reading the chapter. Normally we have a test after every chapter, but because chapter 1 was the math behind the physics, we didn't have a test. Okay, so you're just doing questions 1 through 9 at the end of chapter 2. When you're not doing the exercises, you're doing the questions on the bottom of page 34. Okay, bottom of page 34, 1 through 9. That's it.